Hello everyone, welcome to my civil engineering YouTube channel. Please subscribe to this channel and hit the bell icon to get notified when I post my new videos. Today I'll be discussing the relation between load, shear force and bending moment. So here I have considered a simply supported beam wherein it is loaded with a uniformly distributed load of magnitude equal to W per unit length. So here you can just observe that I have considered two sections 1 1 and 2 2 which is having the interval between the two section as equal to dx, and 1 1 section is at the distance of x from the left support, that is from the support A. So here let me consider F is the shear force acting at section 1 1, and F plus dF is a shear force which is acting at the section 2 2, and M is the bending moment which is acting at the section 1 1, and M plus dM is the bending moment which is acting at the section 2 2. So as the distance varies, the shear force and bending moment also varies. So therefore the shear force at section 1 1 is equal to F, and shear force at section 2 2 is equal to F plus dF. So the variation between 1 1 and 2 2, the shear force variation between 1 1 and 2 2 is nothing but dF. So similarly dm is the bending moment variation between the section 1 1 and 2 2. So next I am going to consider the force and moments acting on the length dx of the beam. So the force F is acting vertically upward. You can just observe here in the second sketch here, the force F is acting vertically upward at the section 1 1. The force F plus dF is acting in the vertically downward direction at section 2 2 in order to maintain in the equilibrium state. So similarly, you can just observe the load W is the load which is acting. So if I want to consider the magnitude, the effect of load between the section 1 1 and 2 2, which is at the distance of dx, so the load will be equal to W into dx, W into dx, W into dx, wherein W, as I said, that it is a uniformly distributed load. So in order to convert this uniformly distributed load to the concentrated load, we need to multiply to the load to the distance to which the load is acting. So we are supposed to take the distance as dx, which is between 1 1 and 2 2 section. So multiply with that of the magnitude of load W. So therefore the load is equal to W into dx between the two sections. So next is the moments M and M plus dm acting at the section 1 1 and 2 2. So you can just observe M and M plus dm, so which is acting at 1 1 and 2 2 sections. So this is the pictorial representation of the assumptions. So the portion of the beam of length dx is in equilibrium. So therefore the portion of the beam of length dx between the two section 1 1 and 2 2 is in equilibrium. Hence we need to resolve for the equilibrium of vertical forces. So therefore I just take upward direction forces as positive and downward forces as negative. So therefore if I just substitute the forces, so we have the forces in the upward direction as F. So we have the force in upward direction as F and downward direction as F plus dF, along with the force due to UDL as W into dx. So therefore F minus W dx minus of F plus dF. So equate that to 0. So it is equal to 0. Why it is a minus sign? Because I have taken downward forces as negative and upward forces as positive. So by resolving and simplifying all this equation, I'll get minus df is equal to w into dx. Minus df is equal to w into dx. So therefore, if I just simplify again further, so I'll just get df by dx is equal to minus w. Df by dx is equal to minus w. This means that if you differentiate the shear force with reference to the distance, so it will be equal to the load acting on the member. So differentiation of shear force with reference to the distance to which the load is acting, it will give the result as load itself on the member. So this equation, it shows that the rate of change of shear force is equal to the rate of loading. So equation shows that the rate of change of shear force with reference to the distance is equal to rate of loading. So this is the expression relation between load and shear force. Now the next thing is, we are supposed to take the equilibrium of the moment. So we are going to take the equilibrium of the moment. So I just take a clockwise moment as positive and anti-clockwise moment as negative. So here we have clockwise moment as m and anti-clockwise moment as m plus dm. So I just make it as negative and this as positive. So next, apart from this moment, we have the moment which is created due to the load of w per meter, which is at the distance of dx. So therefore, first we are supposed to convert this load into point load. So that is w into dx. So there, and then since this is a moment acting, so we are supposed to consider the maximum moment point, that is which is acting at the centroid. So therefore it is exactly at the half the distance in case of UDL. So it is equal to dx by 2. So therefore w into dx by 2 is the moment due to the load acting, that is w is a load acting at the distance of dx. So apart from that, we have shear force which is acting at the distance dx, which is taken as f into dx. Since it is in the clockwise direction, I have considered it as positive itself. So after simplifying all this, I will get the equation as f into dx is equal to dm. So therefore f is equal to dm by dx. I just neglect the higher powers of smaller quantities. I need to neglect the higher power of smaller quantity. So therefore at the end, I'll get the expression as f is equal to dm by dx. So this states that the differentiation of the bending moment with reference to the length gives the shear force. The differentiation of bending moment with reference to the length gives the shear force. Or we can also state that the rate of change of bending moment is equal to shear force at the given section. So therefore we can straight away tell it as the differentiation of bending moment with reference to the distance gives the shear force, and differentiation of shear force with reference to the given length will give the load. Or we can also state it as the rate of change of bending moment with reference the rate of change of bending moment is equal to the shear force, and rate of change of shear force is equal to the load to which it is acting at the given section. Thank you for watching. Please like, share and subscribe the video. Thank you.